Welcome everyone to the first NPI seminar of 2021. Just to remind you, we do this roughly once a month during the academic year. And the goal is to just highlight work that's being done by folks involved with NPI. Usually we run for, sort of short seminar length, so not a full hour, but comfortably more than, say, a conference talk. And feel free to ask questions during the talk. And this month, we're delighted to have Ryan Doenges from Cornell. Ryan's going to present some work that we did with a large team here, as well as Santiago Bautista from ENS Ren. I'll let Ryan introduce everyone. And what this work is doing is giving semantics to the P4 language. Ryan is a fourth-year PhD student, broadly interested in programming languages and verification and distributed systems. So this project is right up his alley. So take it away, Ryan.
Thanks, Nate. So yeah, today I'm going to talk about Petr4, formal foundations for P4 data planes. And this was this presentation sort of came out of a POPL publication. So if anything is a little out there, let me know. I tried to make things make more sense in this context, but I don't want to alienate anybody. This is joint work with Mina, Santiago, Alex, Newton, Samwise, Rudy, Alea, Amanda, and Nate. Many of these people are undergraduates who have gone on to grad school careers or doing a master's. Mina is a postdoc and still on the project. And this is ongoing work, a lot of this. So the problem here is that data planes, broadly construed, kind of lack a formal specification. The internet and data plane protocols used on the internet are specified by the IETF, and they were sort of designed in this IETF working group process. And the way that worked was that you had rough consensus and running code as the kind of gold standard that you had to reach before you could enshrine something in a specification. And this worked great for the internet. Internet protocols are pretty much correct. They are reliable. They've been in use for a long time. And there aren't really, aside from tinfoil hat theorists, nobody really thinks that IP, for example, has bugs, has the correctness bugs in the data plane portion. But today, networking has flown the IETF nest, and network owners, not standards bodies, are the ones driving new data plane development. New protocols are getting developed internally in walled gardens without the benefit of this IETF process. And this is manifested in areas like network virtualization, congestion control, in-band telemetry, and in network computing. These are all areas where there are new data plane protocols being designed, where previously everything was kind of a fixed suite designed for internet use. And the languages these things are being written in vary wildly. So there are things like eBPF, which can be run inside the Linux kernel. P4, the subject of this work, which can actually be compiled to many targets, but is most famous for its role in programming new programmable switch hardware. And also BlueSpec or other hardware description languages like Verilog, which are used when you want to implement your data plane protocol on silicon or an FPGA or whatever you like. And we've chosen to study P4 as a way to get semantics for data planes in general and foundations for data planes in general. And the reason for this is that you can compile P4 to these other languages to be a little, to put perhaps too fine a point on it. But what's also nice about P4 is that it's architecture independent. It has this notion of backend and architecture, and it's retargetable in a way that things like eBPF or BlueSpec really aren't at all. So what I'm going to tell you about in rough order in our search for foundations for P4 is going to be a short example of introducing the language. I didn't get a good look at the list of people in the room, so I actually don't know who's here. So I don't know if everybody knows P4, and I'm just going to review it for you. If you do know P4, it's P416, not P414. Then I'm going to get into our semantic archaeology method, the way we took P4 as it existed and turned it into a formal artifact suitable for mathematical reasoning. And then I'll show you the Petr4 core calculus, which is a simplified model of P4 we use to show some meta theorems, as they're called, about the language, to show that the design of the type system, for example, is sensible. And finally, I'll show you the implementation and a little demo. And I want to emphasize that the implementation, which you can see on the left here, is available on GitHub. It's open source, and I encourage you to try it out, especially if you're interested in building tooling around P4 or verifiers for P4 or whatever. I think it's a great platform to build on, especially if you've ever worked with the alternatives that are available now. I think it's an improvement on the state of the art. So let's get into this example. What I want to do is show you a source routing and ACL program. So there's an ACL on each host here, or each switch rather, which has a simple firewall, source destination sort of firewall rules. And there's a source routing protocol. The way source routing works is your packet, which looks something like this, includes a list of hops. And at each switch, or each hop, if you will, you look at the list of hops and you send the packet out the appropriate port. So here, the first hop is 2. So you send the packet out port 2. You get to the next switch, the next hop is 3, you send it out port 3. And finally, it's 3 again, you send it out port 3. So it gets to its destination. And it's called source routing, of course, because the source specifies the route, rather than specifying, say, a destination and expecting the network to know how to route the packet to its destination. So we're going to program this protocol on a pipeline model, which is what P4 is good for. And the idea is that you begin with a packet, a bunch of binary code, or whatever you like, and you parse it into a typed representation. So you start by looking at the packet and deciding what each chunk of it is. And once you have that, then you perform your forwarding logic. You do sort of your business logic. So you decide where you're going to forward it. Maybe you change some values in the packet. And then finally, you turn it back into binary to send it back over the wire with a deparser. Right. So P4 lets us program each of these stages in turn in separate pieces of code. But before we can do that, we'll have to start by specifying our typed representation so that we know what's connecting these three stages. In P4, that looks like this. We specify our headers as a sequence of types. For our purposes, things are going to be really simple. This is not a real protocol, as you can see. There's just a type tag, which says what kind of packet it is. There's a list of up to 10 hops. So at the bottom here, you can see hop t brackets 10, because there's 10 of them. And then a standard T header, which is sort of a stand-in for IP or Ethernet or something, which is a source and destination. And I'll get into the hops in a moment here, since the next thing we need to do is specify how to parse these things. P4 has an interesting parsing language. So it's a state machine language. You actually write down these little state constructs. And in each state, you can extract some bits out of the packet into a given header and then branch on the contents of the header. So you go from this binary string to a full parsed packet. You start in the start state and you say, okay, extract the type tag, since that's the first thing. And then transition based on that tag to another state. The hops field is going to start by extracting one hop. And then it's going to branch on the bottom of stack flag in these hops. You can see that they're each 2 bytes. The first byte is the actual port that you're forwarding based on. The second byte is this bottom of stack marker. Think about it like a C null terminator. So it's going to keep parsing until it finds something with a bottom of stack marker set to 1, which it does at the end here. And it goes on to the parse standard state, which will just parse out these source and destination addresses. So as you can see, we're done parsing. We've transitioned to the special except state, but there's still some packet left. That's the payload. It'll get saved on the side for later. So it'll just travel next to the packet in the pipeline and get tacked onto the end when we deparse. Moving on to the transformations we want to do, we have an ACL table and some logic for doing the source routing. Remember that, so the table is another unique P4 construct that makes it different than other programming languages. And the way a table works is it lets you specify a sort of match action table without specifying the contents of the table necessarily. So you can say, I look at the key header standard source and header standard dest. So I look at these fields and I decide whether to allow or to deny the packet, which is what this table says. And this table actually specifies its entries statically. So it says, I have one entry, which is if it's going from CC to DD, drop the packet. And otherwise, sort of the default action, just allow the packet. And we can see this running on this packet. The table is sort of declared, and then it's used inside of the pipeline at the bottom here, where it says ACL.apply. But we'll see that happen. So the first thing we do is the source routing logic. You look at the first hop, you look at the port, and you set your egress spec, which is basically the egress port. You can also set it to special values to indicate dropping the packet. So you set your egress spec based on that. So now it's 2. And then you pop it off the stack. And then if the list was empty, you would want to change the type tag so that the next parser didn't try to parse the hops. Doesn't apply here. And then you apply the ACL. And it's going to look at all the contents of the packet and say, OK, because your source is AA and your dest is BB, you don't match my one rule, my one const entry. So the packet should be allowed. And that brings the business logic to a close. We move on to the deparser. There's really nothing to deparsers. You just specify the things you want to omit in order, and then it does it. So in this case, it's type hops standard. All right, so that's the program. Are there questions about this so far? I can get into some more detail on what's going on here, but
seems like we can keep going.
all right. So this program that I've written down is actually broken or subtly broken. Now, if you have a packet like this that has, so you have an attacker at CC who wants to send a packet to DD, there's actually a way to do it. And the trick is to mess with the parser. So lie to the parser about where the bottom of the stack is. This packet has a single hop. It goes 2 with bottom of stack marker 0. And its standard header goes from CC to DD. So you can see it's 0. And this will actually get parsed like this. So it'll fill up the hops buffer, which is up to 10 here. And the rest will end up in the payload. And the standard header will never get initialized. Now the forwarding logic on the switch is going to get an uninitialized header here. And this is a problem in P4 because it means it could actually return anything depending on your implementation. So, sorry, I lost my slide. The P4 specification says that if a header is uninitialized, reads from it can return anything. So this could slip through the firewall and still arrive at DD because the first hop would get executed. And then it would end up at the destined machine. And what's interesting about this issue is that it's kind of implementation dependent. The exact value returned by an uninitialized header can vary across different P4 implementations. So if you write your verifier that helps you look for bugs like this against a particular implementation's behavior, it might not work for other P4 implementations. So this is kind of motivation for a semantics for P4 or a definition of P4 that incorporates these architecture-specific behaviors without specializing to a particular result, so that verification tools can be more portable. And once you have these foundations, there's lots of other interesting work you can do. The most obvious thing, which I've been alluding to in this introduction, is program verification. You can produce foundational architecture-independent verification tools that can get you results and check for bugs across different backends or without specializing to the particularities of some given architecture. But you can also verify compilers. Once you have semantics for the entire language in a formal setting, you can actually go ahead and start proving compilers correct. These can be compilers to any target you also have semantics for, so you do need semantics for your target language. But things like eBPF, C, or even hardware can all be addressed in this way. And besides these verification benefits, there's also informal results you can sort of glean from this process. The specification of P4 is a large and living document, and it's come up against sort of problems in some situations where they don't want to, like the committee doesn't want to enshrine something in the specification that's actually going to turn out to be wrong or turn out to have bugs or make the type system difficult to implement. And having a formal artifact describing the language can hopefully help smooth over these kinds of decisions, because you can actually say, look, I went and I added the feature to the language and I reproved all the old theorems about it. So these properties are still going to work and we don't have to worry about that so much. And it lets you get kind of a clear yes or no answer about things that were otherwise quite murky. Petr4 itself consists of a reference implementation and core calculus. This slide is a little out of date. There's some new code that's kind of exploding into the repo lately. But the reference implementation is a clean-slate interpreter in OCaml. So it's a P4 interpreter. You shouldn't run this in production or really anywhere where you need the packet to go fast. It's an interpreter. It's meant to be kind of a reference implementation, a reference definition of the language. It's parameterized over architectures, and it captures some of the architecture-specific behavior I was alluding to. And it's been validated against an existing test suite in the P4C compiler. So it matches up with P4C, except for things that we didn't want it to match up with P4C about. I can get into this later. But it's more or less compliant with this standard according to these tests. Then there's a core calculus. This core calculus is written down on paper or really LaTeX, and it includes a termination theorem for the language and a case study in language extension. So it sort of models the informal language design uses of this work. And I will mostly spend time on the process to produce these in this talk. And then I'll go into the calculus and the implementation, as I said earlier. This process we refer to as semantic archaeology. P4 exists, it's already out there. What we're doing is not defining a new language or cooking up a new calculus based on purely theoretical considerations. What we're doing is we're going out into an existing artifact with our kind of, as PL researchers, so I know this is not a PL audience, perhaps, but I'm walking into a large networking project and community with my sort of PL taste and PL expectations. And I spent a lot of time trying to understand what I found on my terms, but also on the terms of P4 and the P4 community, and what a networking programming language needs to be in order to be attractive to network programmers. And I found this a really interesting experience because there were a lot of situations where I would dig and dig and dig and try out new examples and try out new things and just be more and more confused as I went, because things weren't exactly how I expected, or things weren't set up in a way that I would have set it up, which is sort of a, it's embarrassing as a theorist to be like, oh no, I'm walking into this situation applying my own rules. So I tried to kind of, I think this was a good experience in controlling the, like learning to use the PL taste without stifling the actual, without hiding what's really going on in P4. This is maybe a little too reflective, but what this actually looked like on a day-to-day basis was quite cut and dry. P4 is defined, depending on how you look at it, in a specification or in an implementation. And the specification is about 160 pages if you print it out. It's available online. It's actively updated. We worked against a version that's, I think, like we're maybe a little behind what the published version is now. And then there's this open source compiler, which is a large C++ project, or to me, a large C++ project. And neither of these is really a useful artifact for formal reasoning for various reasons. One reason is that the spec is written in English, a human language with human shortcomings. And the other reason would be that the implementation is maybe too good, too useful, and it's a compiler, which is not a great way to understand a language. Really what you want is an interpreter or other semantics that are kind of straightforward and define exactly what the program does. And a compiler tells you how to transform the program into some other program that should probably do what the source program does. So it's not a great artifact either. And what we would do is we would go through examples and see what the spec said, or what we thought the spec said, and see what the compiler did with them. So this is going to be a little program. It's sort of contrived. Many of them were quite contrived, but that's how you find the nasty corners of a programming language, is by doing stuff like this. So this is a function, f, that takes 2 arguments. And in P4, things have these direction annotations, out and in out. And it assigns the one argument to the other. And it's generic, so it takes a type parameter t, and the arguments both have to have that type t. Then there's this constant 16. And then there's a main function, and P4 programs don't really have a main function, or they tend to use different control constructs to represent the main entry point, but this is just a function. So here we have a bit of width w, a w bit integer x, and a 16-bit integer food. And what we're going to do is call f with x and mm. Now the question here is, does this program type check? And if so, why? And how should we implement it? How should we specify that? The first thing I see is that we need a type inference algorithm. So you can see that f is generic. And at this call site, you need to figure out what the type argument is. And pretty much all languages with generics have this kind of mechanism. It's what makes it possible to write programs in them without tearing your hair out. But they're often a source of subtleties, inconsistencies, bugs, whatever you want to call it. They're tricky and they're hard to get right. So we wanted to figure out what this type inference algorithm was. The next question that comes up almost immediately is, when are two types equal? And equality is a perennial problem in programming languages because you have to distinguish between the syntactic thing that the programmer wrote down and what they meant, or what sort of how it should be considered within your system. Here you can see that X has type bit brackets W, so a W bit integer, and has type bit 16. And I would argue these are the same because W is equal to 16 and it's a constant, so it shouldn't really matter. But you can see that they're syntactically distinct. So clearly there's more going on here than just comparing them as syntactic objects. And then there's a question of when compile time evaluation happens, or how you simplify these types. Since a good way to compare two types for equality is to simplify them into some normal form or standard syntactic form. And here you can see W should be replaced with 16, and now you have direct equality of these two things. And you can fill it in as a type argument. Are there any questions about this example before I go on? I think I'm not used to giving a talk without an audience, so I can't tell if people are nodding along or staring at me in disbelief. Okay. Let me continue then. There's nothing. Yes, there's this. There's also casts, so I skipped something. These numbers, this is all like super nitpicky, but these numbers, 0 and food, are integers, an int, and the int type doesn't have a width. So in P4, most runtime, in fact, all runtime numbers need to have a specific width, because you can't just be walking around inside of an ASIC with infinite precision integers. It simply isn't done. So you need to say that these things have a width. And one way to do that is by casting them to the appropriate type. And more generally, implicit casts are inserted in all kinds of places in P4 programs. You can think of this as a subtyping check, if you want to think about it like that. But ultimately, you're actually changing the syntax of the program and inserting these things during type check. And all of this is interleaved, as you can see, because each step here kind of depended on the previous ones. So generally, what is P4's type system? How do I come up with the stuff that I was doing on the previous slide? There's a lot of verbiage in the specification about various things. Stuff like these two operands need to have the exact same type, but these need to have the same type. And do these different phrases mean the same thing? Is it defined anywhere? It's not. It's left undefined. And this is the case for many aspects of the type system, which is mostly treated as an afterthought in a specification largely concerned with operational behavior. And the implementation does include a type checker, but it's sort of ad hoc and even overpowered at times. So the inference algorithm used for type inference and filling in type arguments is one that was developed for functional languages like ML, like OCaml or SML. And P4 is just not that sophisticated. So you would hope that there was a simpler answer, or something more easier to understand and less restricted. What we ended up with, and one of the parts of Petr4 that I'm the most proud of, is a pretty nice type checker. And what it does is it goes from a surface AST, which looks a lot like the syntax of the program the programmer wrote down, to a typed AST that has all the simplification and insert cast insertion and all this inserted into it and annotated with types, which is a really nice thing to have later if you want to write compilers, static analyses, whatever. You want to have this type information. So the type inference algorithm is in the style of local type inference. I have a citation here. This is maybe a Popl artifact, or an artifact of this being the afterlife of a Popl talk. There's a coercive subtyping check, which inserts these implicit casts. There's type equality defined on simplified types or canonical types. And then there's a compile time evaluation that simplifies types. And what I think is interesting about this is that all of these things are actually interleaved. You can't write them as separate passes because each one can require calls into the other ones. You end up with this large intermixed kind of type checker, which is interesting because you would think a network programming language wouldn't have too tricky of a type system. But P4 is actually quite sophisticated, which I think is pretty neat. Now we want to talk about operational behavior. So that's the type checker. And again, I'm happy to take questions if there are questions about the type system, but I can move on. Evaluation is a little easier to, it's both easier and harder in different ways, because you can, of course, actually run the program and see what it does. And that's a great way to answer questions about what something should evaluate to. But it's hard because a program might have a lot of different possible inputs. You need to say something about all of them in your interpreter. You're really deciding how all programs should evaluate. So tests can only get you so far. So this is the same program as before, with the type checking done. So you can see the implicit cast are here, the type argument is here. And our question is, what are we going to get at the end? And what do we get when we go into F? So one aspect of P4, which I touched on, was these out and in-out annotations. And something being marked out means it's basically only there in order to be assigned to. But this program is reading from X. So is X going to be uninitialized? Is it going to be just an arbitrary value? What is it? Is it going to be 0 every time? And then after the assignment, what will Y be? Is it going to give it something different from X because uninitialized values are non-deterministic and mysterious? Or is it going to always give it 0? What's the deal? And then since this function call is operating on X and MM, what are they going to be after the call? So is MM going to be copied, modified, and discarded? Or is it going to be modified like as if it was passed by reference? So are we going to see the update to MM after the call to F? And again, we turn to the spec and to the implementation, and there's still a lot of questions. It does say that out parameters are uninitialized, so it does answer that question. But what's tricky here is that architectures can make decisions about operational behavior. And this is basically to accommodate optimizations and accommodate efficient implementation strategies that don't have to consider bizarre edge cases in what I think most people would consider buggy or incorrect programs. And programs that are wrong are allowed to fail in spectacular ways. And then the implementation will make these assumptions or will determinize stuff that the spec says. So the spec will say the implementation is free to do something within this range. It doesn't have to return exactly 0 every time. If it's a bad program, it can be any value. And then the implementation will sometimes resolve this. So the implementation will say it's going to be 0, or it's going to be the previous value. And so lose the architecture independent character of the specification, which we didn't want to do. We wanted to retain as much of this as we could. So what we ended up with in this case was a pretty standard looking interpreter. There's a heap, store, and closures to implement scope and mutable state. And this copy in, copy out calling convention is implemented directly. The compiler handles copy in, copy out, I think by translating it away. I could be wrong about this. I haven't looked in a bit. But this is just to say that we implement it directly rather than translating it to assignments to temporary variables or anything like that. And then the whole thing is parameterized over what we consider the architecture's responsibilities. It's things like resolving the values of uninitialized reads, implementing external objects. So any special sauce that your architecture offers to P4 programs is going to be defined in this separate architecture code, and much more. And you can see the paper for details, or go into the repo and check out the specification for architectures, for targets rather. So as a whole, the implementation includes something I didn't mention yet, which is a parser. It's very important if you want to write any programs at all, which we wrote using an OCaml tool called menhere. This actually uncovered some ambiguities in the published grammar. So the P4 spec includes a grammar for P4 as part of the specification, which is really nice. And there were some ambiguities in parsing where something could be interpreted as two different, in fact, very different programs depending on how you interpreted the grammar. There's also a web-based interpreter, which I'll show a demo of, and a simple front end. So we can run P4C's tests. So we can run the existing implementations test suite to see if we measure up. And it supports separate specification of match action table configuration. So you don't just need to write const entries, you can include it as an input. You write down your program, your configuration, and your input packet, and they're all separate, and you can change them independently. Okay. Then there's the core calculus. I'm just going to zip right through this. Basically, this is a mathematical description of P4 that's very simplified. So it's the syntax looks different, but we tried to capture the interesting parts. A selective transcription would be the tagline of what we did in the implementation. This was basically for the purpose of proving theorems. And prove theorems we did. I've graded some stuff out here. This theorem basically says that if something type checks, if your program makes it past the type checker, then running the program in an appropriate state, initial state, will terminate. So all P4 programs are terminating. And the resulting value will have the right type. So if you had some large expression that type checked as an integer, you'll get out an integer. And this is a reasonably straightforward proof, but quite involved because of the size of the language and some semantic features that I won't get into. Note that this is not true of a language like C, even if C had a very nice type system, because it has loops. P4 has no loops, so everything terminates. P4 is not Turing complete. We also did a case study with this of adding unions to the language. So we extended our language with new features. What I have here is unions, and you can read this in the paper. But the motivation for this was that a proposal for adding unions to P4 had actually violated type safety. So it had broken kind of an important language feature or an important language property because of how it was set up. And this is the kind of thing where having a formal definition of the language makes life much easier. You can actually prove a theorem that says that your translation works, or that your new addition to the language can be compiled back into the old language. You're not adding anything new, and you are not breaking the old type system or type system theorems. And then we did actually test our semantics. All of this was done basically by comparison to P4C. It's got about 800 tests. And we pass all but 10 of them, which fail due to reasons like we don't support the architecture, we don't support more exotic language features, or we just think that P4C is wrong. And according to our reading of the spec, the test is, testing the wrong thing. You can see section 5 of the paper for details or go download the implementation and run the test suite to see the results. And they should look like this. And if they don't look like this, you can file a bug, and I will be happy to look at it. We also wrote some evaluation tests of our own, since P4C's test suite is mostly geared towards regression testing. So it's a bunch of weird things that exercise corners of the compiler. And we needed some tests just for basic stuff when we were first getting started, and for corners that we were concerned about. So that's the tested semantics. And now I want to show a demo. And I've pre-recorded this because I didn't want to mess around with doing a demo over Zoom.
Hey, Ryan, we don't have audio for the demo, so I think you have to share your screen checking the send computer.
Okay, let me.
Why don't you just restart? Yeah.
Yeah. Sorry about that. Next, I want to show you a demo. P4 runs in a web browser thanks to JS of OCaml. And the web page and the web interface look like this. There's a P4 program here, which is written in a nice text editor. And there's a box for writing in your input packet in hexadecimal. This is white space insensitive. These spaces don't mean anything. What I have here, if you haven't noticed already, is the same example from the start of the talk. And the packet here is the same packet from the start of the talk. It's got a hop that's out port 2, then out port 3, then out port 3. And if I run this, you can see that it produces a new packet, which is less nicely formatted, but is just the same thing that you expect. And it's gone out port 2. So it tells you the forwarding decision as well as the contents of the packet. And if we run that back through the program again, we can see that it goes through port 3. And then finally, as we'd expect, it goes out port 3. So this is great. But let's return to our packet and try to exercise the bug we saw earlier. And that was something like this. The packet's going across a forbidden standard source and destination link. And it's got a hop that has no bottom of stack marker set. So when we run this, we get out something that still has the CCDD, is missing the hop. And what's happened here is that the hops have been all parsed, or the entire packet has ended up being parsed into this hops array. And you can see this by going to the dparser here. This is the dparser, and commenting out the call to emit for the hops. If we do this, the packet we get will be much smaller. As you can see, it's just 2 bytes, one for the type tag and one for the payload, which was the last byte left over. So that's the interface. It's really good for developing P4 programs. We think it's also useful as a teaching tool. Today, to try out P4, you need to install a software switch, a network simulator, and the P4 compiler, which are all pretty hairy artifacts, especially if you're new to the language and not familiar with the intricacies of some of these build systems and whatnot. So I think this is great for P4 just in general. Sorry, I saw that the video was kind of illegible. Sorry about that. So there's this demo. You can download the code if you want and try it out. The state of Petr4 now is that we're sort of going off in a bunch of different directions using the existing semantics we built as a kind of base for exploration. We've got a cock mechanization that takes all the interpreter stuff we wrote already and encodes it in cock in this theorem prover that lets us do formal proofs about it. And with that, we're building intermediate representations that simplify P4 for use both in verification and compilation. And we're looking at verified compilers and program logics as well. So simple ways to prove programs correct in P4 that aren't just direct reasoning with the semantics, and also compilers that you can trust that have full kind of CompCert style theorems about their correctness. So I'll conclude now. So P4 is a unifying foundation for data planes, but it lacks semantic foundations as the data planes in general. And the Petr4 clean-slate implementation gives unambiguous semantics to full P4 programs. And the calculus captures kind of the essence of P4 for more informal reasoning or pen and paper reasoning, if you want to call it that. Thank you for listening, and I'm happy to take questions or just talk about the work now. Thanks here to all the collaborators and contributors to the project. And I would be very happy if you went and checked out the code on GitHub at cornellnetlab.github.io/Petr4. Thanks.
Thanks, Ryan, especially for doing, I guess all of us who are teaching know how hard it is to give a talk with a bunch of non-video faces.
Yes, so, and I just wanted to say the ongoing work there is, it's living in the same repo, but it's collaboration with folks at Princeton and with postdocs, Tobias, who I think is here, and John, who have both joined the project since I made these slides. And I think I didn't update them, so I'm very sorry.
No worries.
I don't want to run off with all the credit here.
So Jen has a question.
So
yeah, first of all, great talk.
Question.
Thank you. Great talk.
Thank you.
I was just curious if you could tell us any anecdotes of sort of, things that were surprisingly more difficult than you expected, or particular quirks of either the spec or the open source compiler. Like what were sort of some gotchas that are surprises?
Yeah, this is a great question. Some of it I'm not able to recall very clearly, so I apologize. Usually what I do when people ask me this is I start searching for my own name in the P4C GitHub issues. But I remember one thing, we were looking at the type inference because I really wanted like a simple type inference algorithm. We really wanted something that was simple. And we knew that P4C was using this complicated one. And we actually found example programs where you would have two distinct calls to the same function, and it would infer a type argument for the first one and then use it for the second one without looking at the contents. So it was like it was just saying forever, this program, like this generic function is going to be instantiated at integers now forever for the rest of the program. It was a very weird bug. And then I guess there were things that were surprising to me, like there's some confusion about like what happens if you call something twice. The like sort of wisdom seems to be that you just don't do that. Like if you write something down as a callable thing, you should call it only once, which to me is not, that doesn't make any sense to me, but it appears to be how these things are supposed to be used. So the semantics of what happens when you call like a control or a parser twice in a row is unclear. And part of this, it makes sense because like these tables are control plane controllable, and they're supposed to be sort of one hardware unit, and the whole thing is supposed to be a pipeline. So you can't really, it doesn't make sense to say, okay, now run it back through the pipeline again. You sort of want that to be its own program construct. But the semantics there are sort of wonky. Be one thing.
Could I just jump in to expand on your answer a little bit, Ryan?
Yes, totally.
So some of these things are, they appear to be kind of niggling details, but P4 is a low-level language for manipulating bits. So, some of these details really, like that's the program, that's the point. So some of these small things, I think, actually manifest as can manifest in bigger ways. A second point, which which doesn't really, it's not directly answering your question, Jen, but I would say that there's two broad areas where lack of a formalization is holding back the community. And one is just design. Because P4 has never been formalized, it's kind of got a bunch of weird appendages, and someone went off and did a nice design here and another nice design over here, and maybe those two designs don't quite comport, and it's kind of grown unwieldy. And so it's actually, I mean, I sit on the language design working group. It's slowing down progress because we don't know what's going to happen. If we want to do something else, how does it affect these multiple features that were designed, kind of independently? So that's one reason I think the adding type-safe unions is a nice example of that. And then number two, I mean, a bunch of us are now building on Petra, and people like Fabian, who was on this call, have also done work, Fabian Ruffy at NYU, building, a semantics for P4. In Fabian's case, it was using the P4 front end and then building an SMT model. But having these kinds of tractable semantic models is just the way things are done now in other fields. So like at Princeton, Caroline's work and Margaret's work on and others on testing memory semantics for chips, like that work becomes enabled because you can write down a mechanizable model of what they should do and then start testing them. Or even the web, like WebAssembly these days has a type system and semantics, and people are using that. LLVM. So I mean, another answer, why not us? Like P4 is not a complicated language, despite being kind of a large language. Semantically, it's pretty simple, and it just seems like we'd kind of be idiots not to do something like this. And it would sort of pull a bunch of things together to have a sort of semantics we can all agree on, and then having this computational thing that we can use, to do stuff with. That's kind of
it's what I was going to bring up was and I don't, the paper talks about this, but the talk maybe less so. Like plenty of people have studied P4 formally before, and there's lots of great tools for doing things like verifying P4 programs, often by translation to some other language or translation to SAT queries or what have you. And building those kinds of tools involves making implicit decisions about a language semantics. And I think I maybe can't make this case super well because we haven't built verifiers using the Petr semantics, but the idea is that it's much easier to build one of these tools if you have a semantics written down and you're not having to do that and design your fancy verifier at the same time. You kind of want there to be semantics and then the rest of it. But I'm digressing. If anybody has any questions or comments. Yes, Fabian.
Hi, Fabian here from NYU. Nate already mentioned me. So a quick question. This is obviously great work. I've been working on parallel on a similar formalization. And one pragmatic question I had is, why did you write this tool in OCaml? And what were the reasons? Because I really would like to use your type inference or your parser, but it's very hard for me to hook it in using C++ code and right. I'm more closely working with the compiler directly, and so this Rift is making it a little bit harder.
Yes, I can answer your question two ways. One way is I could write some code that pretty prints. In fact, I think we have this code, so we could pretty print the OCaml typed ASC into sort of P4 surface syntax, and then you could like reparse it. So there's a way to do that.
Oh, that is great. That's a really neat trick.
Yeah. So I would have to like send me an email or something, and I can figure it out. It would not take that long because I think we have the code. To answer the question you actually asked me, we chose to use OCaml because we're interested in doing this in Coq. And Coq and OCaml are very similar, of course, because they're both these functional languages and written by almost like written by similar groups of people, so there are similar design choices. So something you write in OCaml, you can often port to Coq without too much sweat. But if you write something in Coq from the start, it's difficult to run it. You can't use libraries. So it was kind of like a pragmatic decision where we wanted something to work quickly, but we also wanted to turn it into Coq later. So we didn't use kind of the existing compiler infrastructure and stuff like that. And it also kind of makes it easier to translate to a paper formalization too, because something written down is like a data type in OCaml with pattern matches to define the evaluation is really visually pretty close to, and conceptually pretty close to, like what you would write in a paper. Although we had to do a lot of that didn't make it easy is what I'll say, but it was easier than, for example, reading a C++ program and turning that into a formalization. So yeah, so there are like interoperability issues that come up, and the best answer I can give to that is that we can usually print out sort of P4 text and use that as the interoperability language.
That's already very useful. Yeah, just so in general, Petr4 is intended to be an interpreter for formal style verification or methods in any sense. So it's not meant to be a compiler or generate anything else. Just
yeah, we're working on some compilers right now. I think two compilers, but the thing I've described in this talk is, yeah, it's just an interpreter to have something written down and something that you can test and use as kind of a guinea pig, rather than something you would use to like run P4 programs on a switch or whatever.
Okay, thank you.
Thank you very much. Yes, Jim, you have a question?
Randy, I really like the archaeology metaphor. I'm curious if some of the people who created those artifacts that you were exploring, in the people in industry, that is, if they taken interest in your work yet, or have they been exposed much to it? I don't know if any industry people are on this webinar today.
My personal exposure to industry has mostly been through bug trackers, which is unfortunate. But so maybe they can answer this question better than I can. But one thing that came up recently was this issue of like one or two types the same type was raised on the P4 spec bug tracker, and I was able to kind of show up and sort of answer the question. Although I don't know where that's gone. You know, a lot of it is like I find a bunch of little problems and I report the little problems and probably get on their nerves a little bit. But then there's this artifact now, which I haven't really spent a whole lot of time doing outreach or doing kind of communication with industry about it. I guess I would like to. Yeah, I don't know. Nate, do you have any thoughts on this one? Since you actually go to these, you're on the committee or a committee. So.
Yeah, I guess, so we just published this paper a couple of weeks ago, so it's just out there, but I think there's a couple of reactions I've heard. One is basically the one that Fabian sort of articulated, like, OCaml, what's that? And you know, I think Ryan's answer is kind of exactly right. OCaml is a great tool for this, and wanting to build a Coq version, which if you wanted the highest assurance, you know, there's a whole community now building that kind of certified software. That's kind of the right way to do it. I would also point out, I mean, other languages that are getting a lot of traction either were first implemented in OCaml or still use OCaml. So I think the first Rust compiler was built in OCaml. Halide, the first Halide compiler, which is now used for graphics processing, was done with OCaml and later ported to C++. So it's not a, doesn't take much to take an OCaml artifact and either marry it to or port it to a different setting if needed.
Mhm.
I guess one other piece of interest that I don't want to reveal anything was said in confidence, but there's another group doing verification of P4 in Europe, and they're working with some large industrial companies, and so they were very interested in trying to hash out like what's the difference between the open source P4 compiler and the spec and Petr4 and Gauntlet and all of these tools that are out there, and so they were talking about creating some kind of sort of site, some sort of arena where you could sort of like have a bunch of continuous integration jobs that are running test suites against all these things and finding discrepancies. And that sounds like a lot of work, but could be really nice to give a kind of empirical way to say, okay, we've got these it's basically conformance testing at scale for purported implementations of the language. I think that could be interesting, and you can imagine situations where that kind of knowing that your program is going to run a certain way portably across a range of implementations could be useful.
For sure. Yeah, thank you.
Right now, there's no P4 conformance that I'm aware of. I know there's been some talk amongst some of the P4 community, and should we be setting up? So the spec is sort of written in the style of specs that in other specifications, other standards, used words like should or must or to differentiate them, and then you actually have certification bodies that will come in and say, okay, your implementation conforms. Right now, P4 doesn't have that, but it could, and so I could also see, something like Petr4 playing a role in that. So we're over time. I see people are dropping off, but thank you all for the questions. If folks have more questions, I think it's okay to stick around, but I wanted to give people a opening to leave if they have to get somewhere else.